Hello everybody, and I'm Mr. Whoops. There we go. I'm Mr. Marshall, and I'm going to be going over problem number 31 with you guys today. So number 31 basically has one mass on a desk or table and another mass hanging off of it, and they're connected with a rope. So first, I want to draw a picture to explain this problem before we go so far as to draw our free body diagrams. So I'll give us two blocks, mass 1, and another block as mass 2. And they are, let me just correct some of this, mass 1 and mass 2, they are connected with a blue rope. All right, so when we try to do our free body diagrams now, we need to be looking at each picture pretty independently. So we'll start with mass 1. We've got gravity, and we've got normal. And I'm going to say that those two are equal because it's not going up or down. Now, horizontally, we can interpret this as saying that there is some friction. Ooh, no, it says a smooth horizontal surface. Smooth oftentimes means that we are, boom, ignoring friction. Okay, so apparently we are now ignoring friction on this, which means the only force that's acting on it is going to be Ft. That's the tension in the rope. Now, so here's our mass 1. For mass 2, boom, all we have is a force of gravity pulling down, and then we have force of tension in the rope. So here's our start. Now we do want to look at what the sum of our forces are for each one, because tension is showing up in both. So tension is going to be this common denominator that lets us connect them. We're going to try to figure out how much tension is compared to gravity next. We don't have any values for mass or anything, but we can say the sum of the forces on mass 2. So is basically tension and gravity. And if I pan up a little bit, the sum of the forces on mass 1 is really just tension. So we're not assuming any of these are balanced, but we can substitute in for tension. Mass 1 is accelerating. Okay, so this guy is accelerating. He's accelerating at a rate of whatever his tension is. So the tension is whatever causes this mass to accelerate. This mass is also accelerating. We don't know if that's going to be the same. So we're going to call this acceleration 1, mass 1, acceleration 1. The other mass is also going to accelerate at a rate of mass 2, acceleration 2. Let me pan over here, and let's see if we can rewrite this in terms of let's rewrite this in terms of tension first. So we'll do tension is equal to mass 1, acceleration 1. So that's a good start. Now we'll write our equation for right here. We can substitute in this part for tension though. Same rope, same tension. So it's going to be mass 2, acceleration 2 is going to cause mass 1 to accelerate at this rate, plus force of gravity on mass 2 is going to be mass 2 times gravity. I'll leave it as a G. All right, and that's because we know this is mass times gravity. All right, so hopefully that's clear. We're basically just substituting in right here. Net force causes a mass to accelerate, so that's why we've got that. And here's the other part. So from there, Ha, somebody just walked in. Anyway, we can continue now. We're pretty much done here. The accelerations are actually going to be equal because they're attached with a rope. So they're both going to accelerate at the same rate. And what we want to do is set this thing, set it up to solve for acceleration. So you need to rework it. And then, acceleration is mass times acceleration, but you'll also solve for the tension force. All the odd numbered problems are in the back, and I'm pretty sure that this is basically, you're leaving this in terms of variables. We do not have a number for mass to solve, so you're just going to leave this as an equation. All right, so 31. Thank you all.